Welcome to Random Maths. In these video tutorials we will be going over finite series. We will also touch upon infinite series when discussing geometric series in video 4. But the main focus of this video playlist will be on finite series. The playlist on finite series will consist of 5 videos. In the first video, which will also be this video, I'll give a basic definition of a finite series, I'll show some examples of finite series along the way, and towards the end of the video I will go over the addition rule and scalar multiplication rule for finite series. In the second video I'll go over the arithmetic series with some examples. In the third video I'll go over telescoping series with some examples, and I'll also show a nice application of telescoping series along with the addition rule and scalar multiplication rule for finite series. In the fourth video I will go over geometric series with some examples, and in the fifth and final video we will look at a real-world application of the geometric series as I explain the mathematical model behind mortgage loan repayments. Let's get started, and this will be the basic definition of a finite series, so let's go. So the first question is, what is a finite series? So what is a finite series? So a finite series is the addition of all terms in a given finite sequence. That's a basic definition of what a finite series is. And so let's explain what a finite sequence is first and foremost. So if we take a function f which maps positive integers, so this n just means positive integers, this like capital blocky n means capital positive integers, to r, and this r effectively means all numbers other than complex numbers, but I wouldn't worry too much about it if you're not sure on what it means. And now we're going to be using r, which is going to be a positive integer because it's inside this set, and we're going to take n, which is going to also be a positive integer. Again, if you're not sure what this means, don't worry about it. We're going to go over it in another video further down the line, but all we need to know for now is r is a positive integer and n is also a positive integer. That's all you need to know. And an integer is a whole number that's divisible by 1. So 1, 2, 10, 100, all integers. 2.5 is not an 4.2, 1.9, pi. These are not integers, so not integers. The reason being is because they're not wholly divisible by 1. There's a remainder. So if you divide 2.5 by 1 you get 2, but then you also get a remainder. 0.5 is a remainder, so it's not an integer. Basically anything with a decimal place afterwards, after the fact, is not an integer. So any decimal number, any fraction, is not an integer. Okay, and a real number though would be all of them plus rational, irrational numbers. It doesn't matter, as long as it's not a complex number it'll be a real number. Okay, so what this does is it maps, takes some positive integer and it maps it and returns a real number. So it could return another positive integer, could also return a negative integer, could also return a fraction, can return anything in the real numbers. Don't worry too much about it if you're not familiar with this notation, but we're going to define a basic function now, and you'll see how it relates to a series. So a series is essentially going to be defined as such. The function for a series will be defined as such. F of r is equal to a underscore r. For r is equal to 1, 2, 3, ... n. So that means the values in the, we call the domain and the codomain, and I won't go into too much details, but essentially what it means is this can be any natural number up to n. So the domain of this will be any, so this number can be any of these. But we start from 1 and we go to n, and the sequence generated by f is, or will be, a1, a2, a3, ... an. Now a general term in this sequence is just ar, because it could be a2, it could be a3, depending what r is. So a general term for this sequence is just ar, and we put underneath for r is equal to 1, 2, to n. So that's generally how we define this finite sequence. Easy, no worries, there you go. So now let's have a look at what a sum is. So a sum is the addition, so let's look at the definition of a sum. A finite series, sorry, not a sum, a finite series to be more precise. So it is the addition of all terms in a given finite sequence. So we're going to just underline that. Let's get the grammar right as well. Let's underline it. Right, so the addition of all terms in a given finite sequence. Well, we're given a finite sequence here. This is a finite sequence we're given, and it's the addition of them all. So a finite sum, or finite series, I keep saying sum, apologies, a finite series is therefore a1 plus a2 plus a3 plus an. And we're going to set this equal to Sn. Now this is going to be equal to Sn, so we can also show the sigma notation for Sn in a minute. This just means the sum of n terms in a sequence. So let's just explain what that means. So this just means the sum of n terms in the given finite sequence, and that is obviously what I've just called Sn. So if I was to do, let's just give you S1 would just equal to A1, S2 would equal to A1 plus A2, S3 would equal to A1 plus A2 plus A3, and so forth to AN, Sn, which is just that. I've already done it, I'm not going to do it again. Okay, so that's great, but we like to use the sigma notation rather than Sn. So let's use sigma notation. Sigma notation, and the sigma notation is as follows. So we just do the sum from r is equal to 1 to n of AR. So AR is taken from the sequence here. This is the sequence here. AR. So we just take values from there and we iterate. So what we do is we go r is equal to 1. So then we do A1 plus, and then we say r is equal to 2 plus, and then we say r is equal to n an. So it literally just means the same as this. It just means add them up until you hit, so go from 1 to n and add them up, and that's the then this is also Sn. This could also sometimes referred to as, so this was also sometimes sorry about that, sometimes referred to as the nth partial sum. Of a series, and that's because sometimes the series are infinite series, which we're not looking at in this video series, but sometimes you have an infinite series and we take the nth partial sum to find out what it tends to. So we can find out what the sum of an infinite series is by looking at what the finite sequence tends to as n tends to infinity. But again, we're not going to look at that too much here. So yeah, so that's essentially what a finite series is just the sum, the addition of all terms in a given finite sequence. So we get a finite sequence defined by a function f of r, and that gives a rule in order to determine the nature of a sequence, because we can't have the terms have got to be, can't be random. Well, you can have random terms, but in order to create a proper series, a well-defined series, a well-defined finite series, we need to be have a pattern to what we're adding up. If we're just aimlessly picking numbers out the air, I mean, what meaning does it have? It's a waste of time. So yeah, let's look at an example now. So basic example, we're going to set f of r equal to r, which is equal to AR. So the middle bit, always in the middle here, that I've just put in a green box, that's always going to be the function. The rest is just the definition. So definition in blue, the function that I've defined is going to be in R. So this means for r is equal to 1, we've got f of 1 is equal to 1, which is equal to a1. Now this function is a very basic function. You take a positive integer r and you return the same positive integer. So this function does nothing. It's just absolutely nothing. It just returns the same value you input. It's a waste of time really, but I digress. F of 2 is equal to 2, which is equal to a2. We go down, f of n is equal to an, or is equal to n, which is equal to n, which is equal to an. So that's a basic series. So the series, finite series, will be the finite series is going to be 1 plus 2 plus n, which is going to be our SM. Now our AR is equal to R. So let's just do a finite series. We've got from R is equal to 1 to n of AR, which is equal to the sum from R is equal to 1 to n of R, because AR in this case is just R. The function returns itself, so R, which is equal to 1 plus 2 all the way to n. Now let's set n to be something. So case where n is equal to 10. So in this case, what do we have? So let's put n is equal to 10. Then we've got the sum from r is equal to 1 to 10 of r, which is just equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Correct? So what we do here is we solve this by just adding it up. There's a quick method to solve this one actually. It's a special series called an arithmetic series, or arithmetic progression. We're going to be looking at that in the next video, but don't worry, we can add this up right now. So we've got 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, 15 plus 6 is 21, 21 plus 7 is 28, 28 plus 8 is 36, 36 plus 9 is 45, and then 45 plus 10 is 55. So we got that is equal to this, which is equal to 55. So in other words, conclusion, we've got the sum from r is equal to 1 of 10 of r is equal to 55. Let's do red, why not, doesn't matter. That's the solution of the finite series. So that's one example of a finite series with a solution. So yeah, that's easy, right? So let's look at the addition rule now and the scalar multiplication rule of finite series. So addition and scalar multiplication rule. So essentially, if we had two different sequences, so if we had the sequence f of r is equal to a of r and g of r is equal to b of r, and and also we've got, like before, f goes from n to r, and also g maps a natural number to a real number. Then we're going to do the addition and scalar multiplication rule. So then we've got two series. So we've got the sum from r is equal to 1 to n of a r, let's say we add each term of the finite sequence up and then add. So this is just going to be equal to what? So we're going to put square brackets around just to so. Basically, this is the addition rule. So essentially, if we add both of these up, so let's look at an example alongside how we do it. To be honest, let's do that before we move forward. So if we have the sum from r is equal to 1 of 10 of r again, and let's say we have another sequence and another sum, r is equal to 1 to 10 of 3r plus 4. Now I've already done the addition for this one. That's equal to 250, and that's equal to 55. We've done this one above, so this has been done above, and this one we know already equals 250 because I've done that outside of this. Sorry, not 250, it's 205. I've already checked this one. So what I'm saying is, if we do basically, rather than, yes, if I do the sum from r is equal to 1 to 10 of r plus 3r plus 4. Now remember, that's also just going to be equal to the sum from r is equal to 1 to 10 of ar plus br, where ar is equal to r and br is equal to 3r plus 4. But what I'm saying is, so ignore that this is going to be equal to the sum from r is equal to 1 to 10 of r plus the sum from r is equal to 1 to 10 of 3r plus 4, and I'll explain why that is right now. So by the way, the sum for this, let's just have a look at this one, because we've only done an example of a finite series where it's a basic series, so we've not looked at a more complicated one like this. So let's just quickly go over this one, just in case you don't really know what it means. If you're not really understanding this series yet, it's good to get examples in. So let's just quickly, off towards the side there, let's just have a quick look. So we've got the sum from r is equal to 1 to 10 of 3r plus 4. So essentially what we've got to do is we've got to put r equals 1 into this here. So r is equal to 1 into this. And what do we get? Well, we get that it equals 3 times by 1 plus 4. I'm going to put it in square brackets again, just because I've already used a bracket, plus 3 times by 2 plus 4, and all the way, so we're going to add, so plus, and then we've got 3 times by 10 plus 4. Okay, so that is going to be equal to 3 times 1 plus 4, 7, 3 times 2, 6 plus 4 plus 10, plus all the way, and then we've got 3 times by 10 plus 4, 34. The middle stuff here, this dot 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 stuff as well, if you don't know what this means, this just means all the terms in between. So you got 13 as next term, then you got plus 16. I've just ignored it and put dot 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 because I don't want to write it all down. But that's what it essentially means. And I've already added this up, so I've done 7 plus 10 plus 34. I've done it on a calculator. You try it as well. So all you got to do is 7. So I'll expand it. If you do this on a calculator, it might take you a while. That's what I mean. I've already checked it. Plus 25, plus 26, 27, 28, plus 31, plus 34. You'll find that adds up to 205. Okay? But also this, and then if you do, so if you also then do, so if you add both of these together, so if you also do the sum from r is equal to 1 to 10 of r plus 3r, so 4r plus 4, that's going to be equal to the sum from r is equal to 1 to 10 of r plus the sum from r is equal to 1 to 10 of 3r plus 4, because this here is equal to this plus this, so r plus 3r plus 4, which is equal to 4r plus 4. So all that's going to be is, because we've already worked them out individually, we already know that 4r plus 4 is going to be equal to 55 plus 205, and the result of that is going to be 260. So we already know that, but why is that the case? We're going to prove it in general now, and that's going to be the addition rule. So I'm just kind of trying to give you some intuition behind what we're doing with the addition rule. So in essence it's the following. All we need to show is that the sum from r is equal to 1 to n of a underscore r plus b underscore r is equal to the sum of just r is equal to 1 to n of just ar on its own, plus the sum from r is equal to 1 to n of just br on its own. That's what we need to show, that's what we need to prove. I hope you understand what I'm trying to get at with the example here, the actual worked example, but if not, just let me know in the comments below and I'll try and explain it a bit better in future videos. This is my first video, apologies if I'm not too clear. So let's have a quick look why this is equal to this. So we've got the sum from r is equal to 1 to n of ar plus br. Let's just do what by definition what it is. So it is going to be equal to a1 plus b1 plus a2 plus b2 plus a3 plus b3, and all the way, I'm not going to write everything down, but all the way to, so we'll have an minus 1 plus bn minus 1 plus an plus bn, and all of that is just going to be equal to, we can split the terms because these are numbers. Numbers you can arrange the order, it doesn't matter, it doesn't change the value because the return, they can be real numbers, so the order doesn't matter. So you can rearrange the order like so. That's an axiom in mathematics, so you don't have to worry about that. But this is just going to be the sum from r is equal to 1 to n of ar. That is literally, this stuff here is equal to that. And this is just going to be the sum from r is equal to 1 to n of br. So again, so use blue this time, this is equal to this. So that's the proof. You take it, you'd look at what it actually is. So we've got this is what it actually is. Then we split it to this, and then this, and we get back this, and then this. And that's exactly what we wanted to show. Last but not least, we're going to show the scalar multiplication rule. So if we take a number k, any real number k in R, then what I'm going to say is if we do the sum from R is equal to 1 of n of k times by AR, that's going to be equal to k times by the sum from R is equal to 1 to n of AR, and that's what we need to show, that's what we need to prove. So we need to prove this. I'm going to prove it below, and it's a similar proof to the one above. You just literally write out what the sum from R is equal to 1 to n of KR is. KAR, so we've got KA1 plus KA2 plus KAN. We factor the K out, so we can do K, this is the same as K multiplied by A1 plus A2 plus AN. We know that this here is equal to the sum from R is equal to 1 to n. Let's do it in yellow writing to keep it consistent. This is equal to the sum from R is equal to 1 to n of AR. So it's K multiplied by that. So that's been proved, and this here has also been proved. And again, we can show real life examples of it. It will be easier to do in future videos because when I talk about arithmetic progression, I can show you how to solve these sums up here a lot quicker, and that's what we're going to be looking at in the next video. So I'm going to quickly before we leave, before I did the sum from R is equal to 1 to 10 of R, and I said that was equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, and we worked it out to be 55. Now that wasn't too difficult, we did it above. So what we did is we took the first two terms, added them together, and we got 3. Then we took the 3, added on the 3, got 6. Then we took the 6, added on the 4, got the 16. Then we put the 10, sorry. Then we put the 10, added on the 5, got the 15, and we just literally added all the terms up manually, and we got 55. Now there's an easy way of doing this, and that is by taking the number of terms, which is 10, dividing it by 2, and then timesing by the first term plus the last term, so timesing by 11. That will come on to 55 as well. So that's an easier way of doing it, and we're going to show that in the next video. Why is it useful? Well, it's useful because if we're doing the sum from r is equal to 1 to 1 million, so we've got to do of r, so we've got to do 1, that is really bad, apologies for that, all the way to plus 999,999 plus a million. So if we were to add all them up, it would take a bloody long time. We could have made a typo on the calculator. There's so many errors that could have been made, but there's actually a nice quick formula that we can use to work it out. So we would still use a calculator for this because it's a big sum, but all we'd do is put in the calculator 1 million divided by 2 times by 1,000,001. And that would give the solution. I've got a calculator here, so I'll quickly do it. 1 million divided by 2 times by 1 million and 1. I've just done it off screen, but it's going to be a very big number. It's going to have like 11 or so terms, maybe, because that could reduce it down. It's going to be a big number, but yeah, I'll explain it in the next video of how you can get the solution a lot easier with what's called the arithmetic progression, which is where this kind of take the number of terms, divide it by 2, then times by the first term plus the last term comes from. And we'll explain that in the next video, and it's going to be entitled Arithmetic Series. Thank you for watching this video on Random Maths. Hope it was useful. If not, let me know in the comments, so give me some feedback, and I'll see if I can improve for future videos. I'm trying to convey the information in a way that's easy to understand, hopefully, and so that you can take it on board and learn quite well. Let me know in the comments below. I'll try and improve the quality of my teaching in future videos. Just let me know what I can improve. Thank you very much, and see you in the next video.